Assalamu alaikum wa rahmatullahi wa barakatuh. Gentlemen, I will just take one slide from previous chapter 1. I updated the slide yesterday after our lecture and then uploaded it. So make sure you have the right one. Okay. What I'm going to just add or explain on the slide is, let me share my screen. All right. So the application areas of fluid mechanics. This is very, very important. Okay. Although I, highlighted some of the application areas of fluid mechanics, but now I'll be more specific. Okay. Pipeline. Now, pipeline systems for water. When we say pipeline, that's the pipe distribution network. Okay. Water distribution network, sewerage system, or gas pipeline conveying gas, natural gas, or petroleum products. Okay, all this, fluid mechanics, the application of fluid mechanics is there when designing such flows. Okay, and piping and ducting network of heating and air conditioning systems. Okay, heating and air conditioning system, they all use pipes as well, and ducts, passages. And then automobile, our cars is full of fluid mechanics, all components associated with the transportation of the fuel from the fuel tank to the cylinders, the fuel line, fuel pump, fuel injectors and carburetors, as well as the mixing of the fuel and the air in the cylinders. Okay, all these are analyzed using fluid mechanics. Okay, and also fluid mechanics is used in the design of the heating and air conditioning system and the hydraulic brakes as well. The hydraulic brakes, the power steering, all those fluids. You add power steering fluid, brake fluid, and all that. They all use fluid mechanics. Okay, the automatic transmission, the lubrication systems, the cooling system of the engine block, including the radiator and the water pump, and even the tires. Okay, they all use the principles of fluid mechanics. On a broader scale, fluid mechanics also plays a major part in the design and analysis of aircraft, boats, submarines, rockets, jet engines, wind turbines, and biomedical devices, cooling systems for electronic components, and transportation systems for moving water, crude oil, and natural gas. So if you look at fluid mechanics, it has really so wide an application. You did statics. You were told that statics is the main foundation of engineering. Yes, then statics is important in engineering in a similar way as fluid mechanics is. Okay, depending on your area. You can see fluid mechanics has cut across many disciplines. In these applications, you can see the application where you have civil engineering coming in, like in the design of water and sewerage systems for an entire city. Okay, this is done using fluid mechanics. Okay, and also open channel concept, flow in open channel, in drainage network. Okay, all the applications to civil engineering. Okay, then you have a lot of application in mechanical engineering as well, like the automobile. Okay, the automobile have the fuel injectors, cylinders, fuel lines. All these are related to mechanical engineering. Okay, and then you have application also in chemical engineering, like the design of natural gas network. Okay, not oil and natural gas network, crude oil and natural gas network. So this is an aspect of chemical engineering, which is also sometimes considered to be under mechanical. Okay, and then you have another area, which is the area of aircraft engineering. Okay, the aircraft engineering, where you have the design and analysis of aircraft, boats, rockets, turbines, and what have you. Okay, this is having to do with aircraft engineering, which is also like an extension somehow of mechanical engineering. And you have the biomedical engineering part, which utilizes the biomedical devices, okay, for, like dialysis. Dialysis, that's the process of like cleaning our blood, okay, cleaning our blood. If one's kidney is not functioning well, so he needs to be undergoing dialysis frequently. Okay, these biomedical devices all use the concepts of fluid mechanics. Okay, so these are the various areas in which fluid mechanics are. Okay, but that is why you see civil engineering has their own fluid mechanics, mechanical engineering has their own fluid mechanics, as well as chemical engineering. They all have their own fluid mechanics. If you add them up all together, I can tell you fluid mechanics, basically, the mechanical engineering is like the main umbrella, okay? Because it applies most of the application areas of fluid mechanics. Civil engineering takes part of it. The area related to water distribution network and wastewater distribution network, in addition to open channel flow. Open channel flow, most especially open channel flow, is a specific area of civil engineering. Okay, and then chemical engineering takes the area of, let's say, they also take the area of the cooling system, the transportation of crude oil and natural gas, which can also be studied under the mechanical engineering area, okay, as well as the aircraft engineering. So you can, by and large, say that mechanical engineering is like the main, will I say, the mother, the main area where fluid mechanics find its greatest application. Civil engineering takes part of it, okay? It takes part of it, and that part is specific to civil engineering alone, okay? You will not find a mechanical engineer usually studying channel flow and what have you, okay? It has to be a civil engineer. Okay, so I find it suitable to make this explanation so that we all understand where we are going and the importance of fluid mechanics in our daily lives. Okay, like I said, I updated the slide. Okay, this particular for chapter 1. Okay, and as well, I am still updating chapter 2 slides. Okay, so after today's lecture, I will upload what I have presented, and then I will keep on updating the slides. Okay, I will keep on updating the slides. Okay, all right. So let's move to chapter 2 now. Okay, yeah, you can. If you have issue, sign out and sign in. I think you're already back. So let me share my other screen. Okay, so in chapter 2 here, we will be looking at the properties, okay, the fluid properties. Fluid properties. Okay, and the significant learning outcomes, from this chapter will be, you will learn conceptual knowledge and procedural knowledge. Conceptual knowledge, the properties of fluid, density, specific gravity, velocity. Most of these fluid properties, you discuss them in physics 101, okay? But here, we will introduce the engineering, because this is actually called, the title of the course will actually be Engineering Fluid Mechanics, okay? Engineering fluid mechanics, because fluid mechanics is also studied in physics. It is also studied under physics, okay? But that is from the science background, from the science perspective. Here we will study fluid mechanics from the engineering perspective. And by engineering perspective here, we will introduce you to most of the application areas of fluid mechanics rather than just the computational aspect, but we'll be introducing you to the design aspect, the modeling aspect. We'll give you all the necessary background that will enable you undertake deep research in fluid mechanics related to design and application of the course. Okay, so these properties are not new to you. Definitely you studied them in physics 101, specific gravity, surface tension, vapor pressure, block models of elasticity. Okay, and then we'll describe the differences between absolute viscosity and kinematic viscosity, and describe how shear stress, viscosity, and the velocity distribution are related, and describe how viscosity, density, vapor pressure vary with temperature and or pressure. And then for the procedural knowledge, we will look up fluid properties, property values and figures, tables, know when and how to interpolate. Okay. Now, before we move on, we would like to start by introducing the system concept, system, state, and property. What do you mean by system? Okay. A system is the specific entity that is being studied or analyzed by the engineer. Okay. A system can be a collection of matter or can be a region, in space. Okay, we call it a system. Okay, it can be a collection of matter or just a region in space that an engineer is interested in analyzing. Okay, like here, like this is a system. Okay, you can see it here. Now, anything that is not part of the system is considered to be part of the surroundings. You can see the system isolated here. Okay, so it's a collection of matter, a region in space. So anything that is not inside the system is called the surroundings. Okay, and the boundary is the imaginary surface that separates the system from its surrounding. It has zero thickness. So this is the boundary. You can see it in dotted around them. Okay, it's the separation between the surroundings and the system. It has zero thickness. It has zero matter. There is no matter, okay, in the system, and it has zero volume as well. Okay, so it is just like a demarcation, a separation between the system and the surrounding. We call it boundary. Okay. For each problem you solve, it is your job as the engineer to select and identify the system that you are analyzing. Okay. And again, later in chapter 5, we will go ahead and expand the system properties to define what is called the open system and closed system. Okay, the open system, which is synonymous with control volume, and the closed system, which is synonymous with control mass. Okay, and there we'll look at boundaries, constant boundaries, movable boundaries, and then explain. Because like in control volume, you have energy and matter can all cross the boundary, while for closed system, only energy can cross the system. No matter can cross matter cannot cross the system. But this will expatiate more in chapter 5. So systems are described by specifying numbers that characterize them, or that characterize the system. Okay, the numbers are called properties. Okay, properties here is like when you take yourself, what are your properties? What are your characteristics? You are tall, you are 70 kilogram, your weight. Okay, your height is let's say 1.5 meters, and you are light in complexion. So all these are your characteristics, which are also called your properties. Okay, so if you look at yourself as the system, those characteristics of yourself are your properties. Okay, so a property in this case is a measurable characteristics. It's a measurable characteristic of a system that depends only on the present conditions within the system. It depends on the present condition within the system. Like now, if you look at yourself as the system, when we measure your weight, you are 70 kilogram now. Okay, who knows? Tomorrow you can increase if you eat more. Okay, if you eat less, I mean, you may reduce, your weight can reduce. Okay, and the state of a system means the condition of the system as defined by specifying its properties. Okay, it's like when you have a gas in a cylinder, you specify its temperature and pressure. Okay, so these are the properties of the system, and the system here is the gas inside the cylinder. Okay, when a system changes from one state to another state, this is called a process. Let's say you are considering ice cube as your system. When you apply heat, okay, or when you allow it to stand, it will change from solid to liquid, okay? And this is a process which is called what? From liquid, from solid, it dissolves, isn't it? It is dissolution, so it changes state. So this is a process, okay? And also when you apply heat to liquid, it vaporizes, or to water, liquid water, it vaporizes to become vapor, okay? And the process is called vaporization. When the properties of a system are constant with time, the system is said to be at steady state, okay? When you are considering at a given point, when the properties of the system are constant with time, you can say the system is at steady state. Steady means constant, okay? It is not changing. If you are considering a volume of a gas in a cylinder, if the temperature and pressure remains the same at a given point in time, then it is at a steady state, okay? Whereas if it changes with time, then at a given point in time, if it is variable, then it is unsteady. Okay, this will expatiate more again when we come to explaining the different types of flow. Okay, this is referring to state, but we can also describe it using flow. Okay, steady state flow, uniform flow, and what have you. Properties are often classified into categories. Two examples of the categories are given. Okay, kinematic properties. These are properties of the system that characterize the motion of your system. That's why it's called kinematic. You have the kinetic energy. Whenever you have kinematic, it's referring to motion. Okay, characterizing the properties of your system in motion. Okay, example: position. Okay, velocity, acceleration. Okay. So all these are properties, kinematic properties, okay? And you have material properties. These properties characterize the nature of the materials in your system, okay? The nature of the materials in your system, like what is their weight, what is their density, their specific gravity. So this is specific to the material, okay? While for the kinematic properties, they are specific because the material gets those properties by virtue of being in motion. You can only have velocity if you are in motion. You can only accelerate if you are in motion, isn't it? Although for position, you can have position even if you are not in motion. Okay, you can have position, but if the position changes with time, then definitely that body or the system has to be in motion as well. Okay. Examples include viscosity and specific weight. These are examples of material properties. Okay. Now, system state and properties. Still on that. So I started, just introducing, telling you about the closed system, which we call control mass with a moving boundary. You have a gas here whose weight is 2 kg and whose volume, it occupies a volume of 1 meter cube. Okay. So if you consider the gas to be the system, okay, so the boundary between the gas and the container is the moving boundary, because this is the piston preventing the gas from escaping. Okay, so this is a fixed boundary. Okay, it is a fixed boundary. When you apply heat here, okay, when you apply heat, the temperature changes, it expands, okay, and it may push the piston up depending on whether it is movable or not. Okay, so if it expands, the volume now increases, it changes from 1 meter cube to 1.5 meter cube, but the mass remains the same. You have the same mass of gas inside. Okay, the mass remains the same. So that's why it's called closed system or control mass. Okay, the mass doesn't change. Okay, the mass doesn't change. But for control volume, usually you have inflow and outflow. Okay, inflow and outflow of mass. Okay, as well as energy. So here only energy can pass through, but mass doesn't pass through. Okay. Now the property of the system, you can characterize the property of the system here, like you can provide the temperature, the volume, the pressure. Okay, so all these are properties of the system. Okay, or in this case here we have mass. Okay, mass and as well as the volume, although the volume changes in the second one. Okay, is it clear? Gentlemen, is it clear? Okay. Now, we will look at the general properties of fluid, okay? We have started explaining about velocity, okay, as the rate of movement of fluid, It is considered very significant when studying kinematics and hydrodynamics of fluids. Okay, it has no significance when dealing with fluids in hydrostatic conditions. Hydrostatic conditions mean the fluid is at rest. Okay, the fluid is at rest. Okay, so we don't consider velocity. We can say the velocity is zero. So it's a special case. And the SI unit of velocity is meter per second, while the imperial unit is feet per second. Okay, and then pressure. Okay, pressure, the SI unit is Pascal, which is a special unit from the name, given to it by using the name of the scientist who worked very well in that area, Blaise Pascal. Okay, and then the derived unit is Newton per meter square. Okay, because of the fact that pressure is usually very high, so we usually use higher values, kilopascal, megapascal. Okay, because practical, like the atmospheric pressure, as small as it is 101.3 kilopascal. Okay, kilopascal. So usually we use prefix, okay, to show the multiple, like kilopascal, megapascal, and what have you. Okay. And then you have the imperial unit pound force per feet squared. Okay. And pressure is, we have started explaining pressure as it applies to liquid or fluid and solid. Okay. Although we will also expatiate more on that. Okay, because pressure, when you're talking about fluid, it's different from when you're talking about solid. In solid, we usually call it the normal stress. In fluid, we call it pressure for water, okay, and gas as well. And for gas, we usually consider it to be constant. For water or for liquid, it varies with depth. It varies with depth also in case of gas, but depending on the elevation, the altitude, the extent, the variation in depth. Okay, if it is not significant, we assume it is constant. It doesn't vary significantly in case of gas. Okay, unless the depth is really huge, it's very big. Okay, so pressure is the compression or stress at a point in a static fluid. Next to velocity, the pressure P is the most dynamic variable in fluid mechanics. Differences or gradients in pressure often drive a fluid flow. Okay, when you have differences in pressure, then that is when you have fluid flow. Okay, you have fluid flow. Fluid flows from areas of higher pressure to areas of lower pressure. Okay, from high pressure point to low pressure point. Okay, and in low speed flows, the actual magnitude of the pressure is often not important unless it drops so low as to cause vapor bubbles to form in a liquid. So this we'll consider also, that is in low speed flows, the actual magnitude, unless it drops, because when you have drop in pressure, below the saturated vapor pressure, when you have flow in pipeline, you have what is called cavitation. Okay, so when it drops below the vapor pressure, you have bubbles forming in liquid. And those bubbles can be disastrous in pipe flow. Okay, this will explain under cavitation. Now, again, in addition to pressure, you have temperature, which is a measure of the internal energy level of a system, of a fluid. Okay, the measure of the internal energy, the total internal energy of fluid. Okay, is the temperature. Although engineers often use Celsius or Fahrenheit scales for convenience, many applications in the text require Kelvin or Rankine. Okay, the Kelvin is the SI unit of temperature without degree. Initially, we used degree for degree Kelvin, but later in the, I think around 60s also, it was removed. Okay, so for Kelvin, we don't use the degree Kelvin, but we use degree Celsius, degree Fahrenheit, degree Rankine. Okay, and this is the formula to convert, to switch between Rankine is this for Fahrenheit. Okay, this is for Kelvin, and you also have another formula relating when you want to convert from Celsius to Fahrenheit. Okay, so there is another formula that connects that. Okay, from Celsius to Fahrenheit. Okay, so more often than not, you have this to be the formula. You know, 0 degree, degree Celsius is degree Fahrenheit minus 32 times 5/9. Okay, times 5/9. And then if you can change as well, you can make degree Fahrenheit to be the subject of the formula here, and it is going to be the degree Celsius times 9/5, and then plus 32. Okay, plus 32. So this is the formula for switching between Celsius and, but the SI unit of temperature is Kelvin. Okay. Now, mass density. Like I said, you know what is mass density, definitely. So who can tell me? Just tell me, what is mass density? You can talk if you so wish. Yes, what is mass density? Tell me. Yes, 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 yes. I can hear you. What is density, gentlemen? Oh, let me check. Can you still hear me? Yeah, what is density? Density, density.
It is mass over volume, right?
Yeah, mass over volume. Mass of system over volume. Good. All right. So let me go back because it was in presentation mode, so I cannot see what you wrote. I have to exit the presentation mode, come back to the application. All right. So mass density, which is rho, okay, is defined as the ratio of mass to volume. Mass to volume at a point, okay, and it is given by, okay, we use the limit notation. Density is when you consider a very small amount of mass, that is delta M, over very small amount of volume, okay, the limit when, delta V tends to 0, okay, that is the instantaneous, or simply mass over volume, okay. So this is like a special case in which you have like the average, okay, when you have the whole body, the average mass over the average volume, okay, where density is in kilogram per meter cube, mass is in kilogram, the SI unit, and volume is in meter cube, okay. So it can also be measured, in the imperial unit, and the representation we use rho to represent mass density. The density of water at 4 degrees Celsius, water has its highest density at 4 degrees Celsius, okay, which is 1,000 kilogram per meter cube, and decreases slightly with the increase of temperature. This is the table A5, okay, which shows the variation of the density of water, okay. It varies, as you can see, when the temperature increases, okay, it reduces, the density decreases. So why does the density decreases with temperature? Why does it decrease with temperature? Who can explain to me? Who can explain to me? Yes, 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 I can hear you, please. Hmm? You can see at 50 degrees is 988, at 4 degrees 1000, at 0 degrees also about 1000. But usually when it turns to solid, okay, that is to ice, the density is usually lower, okay, is lower than that of water, and that is why you have ice floating in water, okay. Okay, we'll come back to this. All right, now this table A2, which shows the density of other fluids, gas, like air. The density of air, 1.2. Very small compared to the density of water, isn't it? I told you, I mean, definitely we know when we explain the molecular arrangement of, molecular structure of solid, liquid, and gas, we know that in gas, the molecules are far apart, isn't it? So they usually have less density. And we said liquid have higher density than gases, while solid has the highest density. Okay, so we expect definitely gases to have lower density than air. And that is why even in computation, when we have, let's say, the density, we have, let's say, density of water minus, let's say, density of air. We normally, ignore the density of air or set it to 0 because it is very small compared to the density of water. You can imagine here 1000 minus 1.22. Very small, isn't it? Very negligible change. Okay, 900 and 998 point something. So it is usually very, very small. Okay, so for practical purposes in computation, as we are going to see in the next chapter, that is chapter 3. When we have gases in our system, we want to find the pressure in the system using hydrostatics. We normally ignore the pressure exerted by the gas. Sorry, the density exerted by the gas because it is so small. Okay, if we are, let's say, taking a difference between density of liquid and density of gas. Air is 1.22, very small. Carbon dioxide, 1.85. Helium, 0.169. Hydrogen, 0.08, very, very light. Methane, natural gas, 0.6. Nitrogen, 1.18. Oxygen, 1.35. All these gases, some of them are available in the atmosphere, isn't it? Who can tell me what are the gases available in the atmosphere? I need to be switching to see what you are saying. Oh, someone is saying, what is the question? Because the molecules small. So, well, tell me the gases available in the atmosphere quickly. You can just tell me or you can type it. I am back to the Blackboard area. Okay. The gases, all the gases available in the atmosphere. We define the atmosphere as the air surrounding us, the available space around us. Okay, what are the gases in the atmosphere? Yes, 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 you have. Just tell me. Like I said, I enabled your mic. Gentlemen. Ya Shabab. Okay. Someone is saying hydrogen. But okay. What else? Oxygen, nitrogen. What else? Repeat
Carbon.
the question. The question is, tell me the gases available in the atmosphere. What are they? Just
Hydrogen, oxygen, and carbon.
and what? Carbon? Carbon is not a gas. Carbon is not a gas. Helium, okay, carbon dioxide, okay, now you are talking. All right, now tell me the percentages now. Tell me by percentage. Yeah, we have oxygen, we have nitrogen, we have even argon, okay, and we have nitrogen, oxygen, carbon dioxide. So
nitrogen 21. Only I know that.
nitrogen is 78%, 21 is oxygen. Oxygen is 21, okay, nitrogen 78, oxygen 21, argon 0.93%, carbon dioxide 0.04%. Yes, good. So these are the correct percentages. Yeah, so you can see oxygen. Who is this asking for bonus? Okay, all right. So 78 and oxygen, 21. Okay, you have trace elements, okay, or trace gases, and the trace gases, they constitute 0.1%, okay, and under the trace gases you have methane, you have helium, you have also ozone. Even ozone, because ozone layer, as we're saying, is all like a gas. We have neon, okay, so all these constitute the trace gases, okay, constitute the trace gases, but we don't have hydrogen because hydrogen is combustible. Okay, if we have hydrogen, it is the sun. The sun is basically made up of hydrogen and helium. The sun, as we see it, is a gas giant. It has only hydrogen and helium. So hydrogen is really combustible. Okay, although it's also combustible, but the percentage as it is now, is what we have that is optimal. Okay, once the percentage increases, then things will just start getting burnt. Okay, all right, let's move on. Does the density of any fluid changes in mole or mass? Now, answer this question. Does the density of any fluid changes in mole or mass? Hmm? Does the density changes in mole or mass? It is not sharing my screen again. It does not change. Why? Okay. Does the density of any fluid changes in mole or mass? It doesn't change because density is mass over volume. And does mass change in mole or mass? No, mass doesn't change. Weight change? Yes, weight changes from planet to planet because of the variation in acceleration due to gravity, okay? But the density of any fluid, okay, change irrespective of where it is, okay? Some useful facts about density. Density varies with the pressure and temperature of the material, okay? Density varies with the pressure and temperature of the material. We have seen for water how it varies. Okay, for liquid, the variation with pressure is usually negligible. Okay, for liquid, the variation with pressure is usually negligible because liquid, you see, density is mass over volume. You have liquid. Liquid, it has tiny spaces between the molecules, but before you can compress it, before you can reduce the volume of liquid, okay, the pressure has to be so huge. That's why we consider liquids to be incompressible, okay? We consider liquids to be incompressible, okay? Because like you need to apply about 210 atmosphere to compress water by 1%. Just 1%. You need 210 atmosphere. That is 1 atmosphere is the atmospheric pressure that we currently experience. So 210 times, and water will compress to just 1%. So that's why for all practical purposes, we consider water to be incompressible liquid. Okay, and the same thing goes for all other liquids. They are usually incompressible. Imagine here now, if you increase the temperature of the atmospheric, if you increase the pressure, or if you change the pressure by just 0.01 atmosphere, the air pressure will be affected by 1%. Okay, the pressure will be affected when you apply just this pressure to air. Okay, its volume is affected. Okay, it got compressed by 1%. Okay, so because of course gases are constantly in motion, so you can compress them together, so they are compressible. The density of a gas is often calculated by applying the density form of the ideal gas law. You know, in this, although fluid, like I said, also refers to gases, but I will not be delving so much into the properties of the ideal gas equation or the gas properties, the gas treatment. Our focus will remain on fluid or water as our main fluid. But like I explained, for mechanical engineers, for civil, for chemical engineers, in which they deal with a lot of systems that has both liquid and gas, or even just gas alone. So they need to, go all the way to deal with the ideal gas equation, the properties of the gases, and what have you. But for the civil engineering application, more often than not, our main interest is on water as our main fluid. Okay. Now, okay, we said density varies with pressure and temperature. Why does it vary with pressure and temperature? Density is mass over volume. This we explained. Okay, it is mass over volume. So what happens when you increase the temperature? Okay, what happens when you increase the temperature? Okay, when you increase the temperature, they will become more mobile, isn't it? They become more mobile. They become more mobile. The gases and the spaces they surround or they occupy, the volume can also increase when you increase the temperature, and also pressure affects the volume. I just explained about the compressibility. It affects the volume. Although for liquid we said it is not affecting it that much for liquid, but it has significant impact on gases. Okay, so if the volume is affected, then definitely density will ultimately be affected. Okay, density will ultimately be affected. Okay, that's why usually at higher temperatures, the molecules are more mobile, they are free to move about. So the volume more or less increases, and when the volume increases, definitely the density will what? Decrease. Okay, because the mass doesn't change, the mass remains the same throughout. But when the volume is affected, this volume is affected by both pressure and temperature. Okay, increase in pressure leads to increase in reduction in volume. When you increase the pressure, the volume reduces, while increase in temperature leads to increase in volume. So if the volume increases, the density will reduce, and that is why you see at higher temperatures the density of water reduces. Okay, I hope you can explain this if I ask you to. Okay, it is very simple and straightforward. Okay, by definition, density mass over volume. Okay, so we'll just take a simple example. Move on. A specific fluid has a mass of 243 kilogram. Okay, and has a volume of 180 meter cube. Okay, so this is our mass. Okay, and this is our volume. Okay, under the atmospheric pressure and a temperature of 12 degrees, calculate its density. Okay, can you predict what is this fluid? So the density mass over volume, simple. Okay, mass over volume. So this is the unit kilogram per meter cube. Okay, and can you predict what this fluid is? We can go back to table 4.1. If this is the density 1.35, 1.35 is oxygen. Okay, oxygen is the one having density of 1.35. Okay, so very simple application. Yeah, the density is the fluid is oxygen. Okay. Now we'll move on to another property, which is specific weight. Okay, specific weight. The gravitational force per unit volume. It is the gravitational force per unit volume of fluid. Gravitational force per unit volume of fluid, or simply weight per unit volume. Because weight is the gravitational force acting on an object, acting on a body. Okay, that is called weight. That is simply the effect of the gravitational force on a body. Okay, or the force of the gravity acting on that body. Okay, so that is weight. So weight per unit volume is the specific weight. In fact, the term specific, when you hear specific, it means it is per something. Okay, per something. Either you're considering mass, 1 kilogram, specific heat capacity, or in this case, specific weight, specific volume, and what have you. Okay, it means per, meaning divided by some, it is per something. Okay, here we have per unit volume. Okay, and we use the Greek symbol gamma for the specific weight. Okay, so gamma is just weight over volume. Okay, weight over volume. It can also, weight is what? Weight is mass times gravity. Okay, volume. Okay, and then what is mass over volume? We just finished explaining mass over volume. What is it? Mass per unit volume. Tell me, what is mass per unit volume?
Density.
Yeah, density. So this is now rho g, isn't it? So specific weight, you either use mass per volume or is equal to rho g. Okay, that is density times acceleration due to gravity. Okay, and the unit weight per volume. Weight is in Newton, volume is meter cube. So definitely is Newton per meter cube. Okay. I hope you are taking note, because like I'll be making, you can see I can write on my screen, making some notes, you know, some which may not be in the slide. Although this formula is provided, but sometimes some of my, you know, explanation, my writing may not be contained in the slide. Okay, so it's better you have your, you know, lesson notebook where you'll be jotting some important things, either those I mentioned or those I wrote down. Like now I explain why density varies with temperature and pressure, which is not in the slide. So, but I explain exactly what happened. Why does it vary? Okay, so water at 20 degrees has a specific weight of 9,790. Okay, and air at 20 degrees and standard atmospheric pressure has a specific weight of 118. Okay, has a specific weight of 11.8 Newton per meter cube. Okay, the specific weight of air. So you can see, because of the fact that specific weight is a function of density, that's why air has low specific weight compared to water. Okay, because it is a function of density. Now specific weight, okay, weight over volume, okay, this explain, okay, this I just, some useful facts about specific weight. Okay, specific weight varies with temperature and pressure. Definitely it will vary with temperature and pressure in similar fashion to density. Okay. The same way, you know, since the specific weight is density, so whatever will affect density will affect specific weight. Okay, so definitely we'll expect the specific weight to decrease when the temperature increase. Okay, and we'll expect it to increase when the pressure increases. Okay, specific weight is common for is commonly used for liquids, but not commonly used for gases. Okay, it is commonly used for liquids, not commonly used for gases. Okay, so why is that?
Because the gases, they don't feel the gravity. The gravity doesn't make anything to gases.
What?
I mean, the gravity doesn't change the gases, so the weight not commonly used for the gases.
What doesn't change for gases?
I mean the mass, because there is no any acceleration for the gravity on the gas.
Oh, okay. Can someone expatiate more on that? Hmm? You know, specific weight, because we say density, okay? Density of gases is usually very small. You can see here, this is just 11.8, this is 9,700. So it is usually very, very small. You know, the specific weight is not significant for most gases, okay? It is very insignificant for most gases. Okay? That's why it's usually considered for liquids, okay? An example here, okay, calculate the specific weight of water in Earth, Moon, and Mars. Okay, hint, gravitational acceleration in Moon and Mars are 1.6 and 3.73. Okay, in Moon and Mars. Okay, so let me ask you one question. By saying the gravitational acceleration in Moon and Mars is 1.6 is 1.63 and 3.73. Based on the gravitational acceleration, which one is heavier? Which one is more massive between Moon and the Mars? Based on the gravitational acceleration, who can tell me? The gravity on Earth is on average 9.81, okay, meter per second squared. So by saying this is on the Moon, 1.63, and this is on Mars. So based on the gravitational acceleration, which one is heavier? Definitely the one with higher gravitational acceleration is heavier, because it means, you know, from the Newton's law of gravity, isn't it? F equal G m1 m2 over r squared. Okay, so m1, let's say mass of planet, mass of the planet. Okay, so if it is heavier, it will have more gravity. Okay, the force of gravity will be higher on the objects around it. Okay, just like Earth. Okay, meaning Earth is heavier than Mars, heavier than Moon. But what about Jupiter? Jupiter, the acceleration due to gravity will be far greater than 9.8, isn't it? Because it is greater, it is heavier than Earth. Okay, all right. So here we want to find the specific weight of water in Earth, Moon, and Mars. Okay, and we just use this formula. We know the density of water, which is constant. It remains the same in Moon, in Mars. Okay, but G will change. Okay, so G here 9.81, 1.63, and 7.3. Okay, so the specific weight will vary, isn't it? Because it's also a function of acceleration due to gravity. Now, specific gravity or relative density. Specific gravity or relative density. Like I said, when you have specific, it means it is per something. Okay, so you have a ratio when you have specific. Okay, so the ratio of specific weight of a fluid to the specific weight of water is called specific gravity. Okay, we use S or sometimes SG to represent the specific gravity. Or relative density is the same word. I mean, the words are synonymous. We call it specific gravity or relative density. For relative density, we use RD. Okay, relative density. Okay, which is just the ratio of the density of fluid over density of water. So we are like comparing the density to water in this case. Okay, our reference in this case is water. Okay, or it's the same thing as the specific weight of any fluid over specific weight of water. So in this case, who can tell me what will be the specific gravity for water? What is? Just tell me so that I can, because I need to exit the presentation, go to see what you write. So just talk. What is the specific gravity of water? Yes, yes. Can you hear me? Yeah, definitely it's going to be 1 because density of water over density of water. So they will cancel out 1000 over 1001. So the specific gravity of water is going to be 1. Okay, so specific gravity is unitless because it's ratio of the same quantity. Okay, kilogram per meter square, kilogram per meter, sorry, kilogram per meter cubed, kilogram per meter cubed. So they will cancel out. So it is dimensionless, it is unitless. Okay, some useful facts about specific gravity. You know, it is equal to 1 if it is water, but then what about if it is less than 1? If it is less than 1, what does that mean? It means the fluid density is less than the density of water. Okay, if it is less than the density of water, then it will float like gasoline, like oil, gasoline. Okay, like the benzene, you know, benzene is less dense than water, but crude oil is heavier than water. So the specific gravity of crude oil is going to be more than 1. So it's going to sink, isn't it? Okay, wood and styrofoam float in air. Okay, float on water. So, you know, just like we explained the density of air. Density of air is 1.2, but density of hydrogen is less than the density of air. And that's why when you fill a balloon with hydrogen gas or helium gas, it will float. That's why you have hydrogen balloons. Because just like, you know, when you have liquid, okay, when you have something whose density is less than the density of water, it will float in water. The same thing with air. When you have a balloon, you know, when you go to the malls, you have some balloons, small balloons for the kids, which is filled with helium. And when you release the balloon, it rises up, meaning it floats in air. Do you understand? And that's because the density of the gas inside the balloon is less than the density of air. The same thing here, when specific gravity is less than 1, it means the density, because specific gravity is the density of fluid or density of water. If it is less than 1, then that means this is less than the density of water. And if it is less than the density of water, then it will float. If it is greater than 1, if it is greater than 1, it means that the density of the material is greater than the density of water. If it is greater than the density of the material, it will sink, like potato, concrete. You know, most solids have density greater than the density of water. Okay, but I told you ice has density less than the density of water, and that's why it is. Okay. If you add oil, whose specific gravity is 0.9 to water, specific gravity 1, the oil will float on top of the water, isn't it? This is because oil and water. Okay, let me check this. Oil and water are immiscible. Okay, meaning they cannot mix. Oil and water are immiscible, meaning they cannot mix, which means they are not capable of being mixed. Yeah, okay, I mentioned it. If you add alcohol, the specific gravity of alcohol is 0.8 to water. The alcohol and water will mix, okay? So it will not float like oil, okay? Fluids that are capable of mixing are called miscible, okay? The properties of density, specific gravity, and specific weight are related. If you know one of these properties, you can easily calculate the other. Okay, if you know density, you can easily calculate specific weight because it is what? Rho g. You know specific weight, you can easily calculate specific gravity because it is, you can either use specific weight or use density. Whichever one will give you the same thing. Okay. Values of density and gamma for water at 4 degrees are listed in table 5.6. Okay, and the values for specific weight for liquids, for specific gravity for liquids are listed in table A4, in the appendix. Specific gravity is commonly used for solids and liquids, but it's rarely used for gases. The same explanation because of the density of gases. Density of gases is usually very low. Okay, the density of gases is usually very low. So imagine having the density, let's say, of air 1.2 over 1,000. So the value of the specific gravity will be extremely small, very, very small. Okay, so it is commonly used for solids and liquids, but rarely used for gases. Okay, so recommended working knowledge here: the specific gravity, petroleum products, e.g., gasoline or oil, they have their specific gravity less than 1, 0.7 to 0.9. But I told you crude oil has specific gravity greater than 1. And again, seawater, that's the water in the ocean, because it has a lot of dissolved minerals, dissolved salts, okay? So its specific gravity is 1.03. It is heavier than fresh water. Fresh water, the specific gravity is just 1, okay? It is just 1. But seawater, because of the high mineral content, high dissolved salt that it has, okay, its specific gravity is higher. And mercury specific gravity is 13.6. You can see very high, higher than that of water. Okay, water is, the specific gravity is 1, but mercury, you know, it is very thick, semi-solid, okay, or metalloid. So for seawater, if I ask you to explain why do we have the specific gravity of seawater higher than that of fresh water, okay, simply because of the mineral content that you have in seawater. It has a lot of dissolved salts, and specific gravity is what? It's a function of mass. It's a function of mass. So if it is pure H2O, you have additional mass in the system, okay, added, then definitely the specific gravity will increase, isn't it? That of steel is 7.8, okay, that of aluminum is 2.6, concrete 2.2 to 2.3, okay. Now calculate the specific gravity S of mercury, okay. The density of mercury is that 133,000 Newton meter. So the specific gravity of mercury, specific weight of mercury over specific weight of water, okay, which is this is in kilonewton, okay. The specific weight of water in kilonewton, okay, which is 13.6. And you can do the same thing to find the specific gravity of any other material, as long as you know the specific weight or the density. Okay. Here it says liquid has a volume of 2.5 meter cube and a weight of 9.81. Okay, so this is the volume and the weight. So what can we do? Determine the specific weight, density, specific gravity of the liquid. So this is very, very simple. The specific weight is what? So the specific weight is weight divided by volume. The density is mass over volume. We don't know the mass, but we can find the mass. Because if we have the specific weight, how can we now find the mass? Okay, or the density, because this is weight over volume, or rho g. Okay, so all this is known, this is known, this is known, so we can find the density, correct? And then for specific gravity, the specific gravity, we can either use the density of the material, which we found here, over the density of water, which is known. So very simple and straightforward. So we found the specific weight here. Okay, this is in kilonewton and this is in newton per, so kilonewton per meter cube is newton, and then the density, mass, weight is mass over volume. Okay, so we found the mass first, This is another way. You know, the method I showed before is also valid. You'll arrive at the same answer. Here we found the mass using weight equal mg. Okay, so this is the mass 1,000 kilogram, and then the density now is 400 kilogram per meter cube, and the specific gravity is just the ratio of the specific weights. Okay, which is 0.4. So definitely this material is going to float. Let me see, what is the material? Is it mentioned? Okay, it's liquid. So definitely the material is going, if I ask you, is the material going to float in water or not? This specific gravity is 0.4, less than 1. So it is going to float if it is not miscible with water. Okay, like oil. If it is like oil, then it is going to float. Okay. Okay, let me see what you are saying, because someone typing. If they equal to each other, what happens? If they equal to each other, then it will be 1. Uh, uh, you usually have variation unless it is the same substance. If it is the same material, then that's when it will be equal. Otherwise, you have, I mean, definitely there will be some slight variation. Okay, more often than not. So variation of liquid density. So let's take 5 minutes break. Okay. Let's take 5 minutes break, and then we'll continue with the variation of liquid density. Okay. So take 5 minutes break. Go and drink water. I mean, stretch out, and then we come back after 5 minutes. Yeah, gentlemen, we're back. Let's move on. Okay. I will try to be uploading the slides before the lecture. Okay. I'll try to ensure I prepare it ahead of time. What happens is because I normally update it, so I will try to finish all the updates, or even if I update anything, then I will let you know. Okay, so that you can follow. And for the recording, I know automatically after every lecture, after some hours, the ITU are supposed to upload it. Okay, so I will check after this class. I will check it to see the previous lecture. If it is not, I will write to the ITU about it. Okay. Now, variation of liquid density. Water has a constant density unless subjected to large pressure. This we explained. And for most applications, liquids are considered incompressible. Okay, that is, density is not changing. This I also explained. And in this course, we shall consider fluids to be incompressible and homogeneous. Okay, that is density not changing with space. Okay, that is we should consider fluids, that is if the fluid is liquid. Okay, but for gas, definitely usually it is, in some instances it may also be considered as incompressible depending on the pressure. Okay, now example 5, it says meteorologists often refer to air masses in forecasting the weather. Okay, if you hear of any weather forecast, they will be referring to air masses. So here, estimate the mass of 3 kilometer cubed of air in kilograms. Okay, make your own reasonable assumptions with respect to the conditions of the temperature. Okay, so the mechanical properties of air, because here we are to estimate the mass, we are given the volume. So we need the density. Okay, and to get the density, we need the density varies with temperature. Okay, so we can select a given temperature. So this is the air density at different temperature. Okay, 10 degrees Celsius if it is cold. Okay, now I know the temperature is about 40 something degrees. So you can choose higher temperature. Okay, so but we specify it, density of air at 10 degrees. If you choose 40, you specify the temperature because it varies. Okay, this is the density, and simply this is just converting the volume from kilometer cubed to meter cubed. Okay, 1 kilometer is 1,000 meter cubed. So it's very simple to convert to meter cubed. Then the density is mass over volume. So mass is going to be density times volume. This is the density we got from the table, and this is the volume provided from the problem. Okay, so the mass is 3.75 times 10 to the power of 9 kilogram. Okay, so we move to the next lecture. Now, properties of fluids. Okay, these general properties: velocity, pressure, temperature, density, specific weight. This is what we considered. Okay, now we move on. Now, pressure and shear stress. Pressure and shear stress. I started explaining these concepts in the first class. When you understand stress, many topics in mechanics become easier. Okay. So here the big picture. The big picture is that there are only two kinds of stress: normal stress and shear stress. Okay, that is, although normal stress and then shear stress. Okay, in fluid mechanics, the normal stress is nearly always just the fluid pressure. Okay, in fluid mechanics, it's nearly always just the fluid pressure. Okay, that's why we prefer, we call it pressure in the normal stress. We call it pressure in fluid mechanics. And then to define stress, we begin by noting that stress acts on material part of it, because it is more or less like the compression. Okay, the compression on the body. Okay, the force due to the compression on a given area. Simple, okay? So we begin by noting that stress acts on material particles. For example, if you bend a beam, the material particles are deformed by normal stress, okay? Examples of pressure and shear stress. So if you bend a beam, the material particles are deformed by normal stress. Okay, if you apply force here, apply normal stress here, okay, it will bend it, okay? So you can see these particles will be compressed, okay, and this will be expanded, okay? So you have compression, some will be in tension, some will be in compression, okay? The materials here at this area, the lower side will be in compression, and the material at the upper end will be in tension. They will be like pulled apart, okay? And that is why later you are going to learn why do we need reinforcement, okay? When you have concrete, if it is concrete is very strong, you know, in tension, but it fails in compression, okay? And that's why, like here, we need to provide reinforcement. We need to put reinforcement bars, okay? We need to put bars that will resist the compressive strength, okay? Sorry, the is very strong is the other way. It is very strong in compression and fails in tension. Okay, so concrete is strong in compression at this point, okay, but in tension it fails, okay, under tension, okay. So that we need to get our reinforcement bars, okay. This will be expatiated more in subsequent courses, probably in structural mechanics. You may begin to do it, most importantly in what do you call structural analysis and reinforced concrete design. Okay. So normal stress, it compresses the materials here. It elongates the materials at the top. Okay. Now, this weight causes. Okay. Okay. Now, when we isolate the material, when we look at a grain, a particle, okay, you apply a normal stress here. You have tangential stress, which is the shear stress. Sorry, tangential force, this normal force, okay? The magnet, yeah, delta Ft is the magnitude of the tangential component of the force vector acting on this face of the material particle, okay? The tangential component, and this is the vertical, the normal component of the force vector, okay, acting, and this is the area, the cross-sectional area, okay, of the face. Now, what is the pressure? Pressure is simply the normal force over the area, okay? The normal force over the area, that is, that constitutes pressure, okay? We use the normal force over the area. Now, for stress, we use the tangential force, okay? Which is delta Ft, okay, over the area, okay? So you can see the normal force over the area is acting on the particle is giving us pressure, while stress here, we look at the tangential force, okay, acting parallel to the surface area, okay, parallel to the surface area, okay, that gives us stress, okay. Sorry, the shear stress. Well, we use tau. This is tau. It's a Greek alphabet, tau. Okay, and like in this case, this weight causes a lot of oil on this in the saying that is 500 kilogram. Okay, added. There is oil here. Okay, the load on the oil causes stress to act on each material particle because this weight is being held by this oil, okay? So it is feeling the weight. It's like you holding like one bag of cement, okay? when you hold one bag of cement, so you will carry all the weight. So your muscles, the particles that make up your body will feel the weight. Okay, so that is the pressure acting. Okay, of course, the pressure, it will not be, the weight over the surface area in contact. Now, general equation. A general equation is an equation that applies to many or to all problems, but then you usually have a special case equation, which is an equation that is derived from a general equation, but it's more limited in because there are assumptions that must be made in order to apply the special case equation. As the name implies, special case. So they are applied to special cases. So you need to understand all this, okay? Voice of the engineer. Learn the general equations and then derive each special case equation on an as needed basis, okay? And the rationale is that there are very few general equations, okay? And it will make your learning simpler and you are less likely to make mistakes because general equations by definition are more often than special case equations, okay? And we have some examples of general equations. The Newton's law of universal gravitation, okay? It's a general equation, and weight equal WMG is a special case equation that is derived from the Newton's law of general gravitation, okay? Because it is simply, F, this is mass of the Earth over any mass, G over R squared. Okay, so G mass of Earth and R squared is now equal to acceleration due to gravity. Okay, so F is now mg. So F, which is now called the weight, and G now in this case, acceleration due to gravity, is the neutral gravitational mass of Earth over R squared. Okay, this is G. And that is why the acceleration due to gravity varies. Okay, on the surface of the Earth, it is usually around 9.807. Okay, when you above at sea level, this is at sea level, meter per second square at sea level. When you go below sea level, it decreases about a distance of 4.5 kilometers below sea level. It decreases. It becomes around 9.83. Sorry, it decreases to about maybe 9.8 or 9.7. Okay. 9.8 or 9.7 something. Okay, it decreases up to a distance of 4.5 kilometers below the sea level. Okay, and then it increases. So, who can tell? What do you think will be the acceleration due to gravity at the center of the Earth? At the center, the core, the very center of the Earth. What will be the acceleration due to gravity of a body? Okay. Now, of course, because it's inversely proportional to distance of separation apart, meaning the closer it is, the higher. That is why, if you are on the surface of the Earth, if you tend to go away from the Earth, the acceleration due to gravity is reducing. Okay, the farther you are away from the Earth, from the surface of the Earth, the less the gravity. And that is why on the moon, you can have a place of zero gravity. If you go, so many kilometers above the Earth's surface, where you have escaped the gravitational influence of Earth, the acceleration due to gravity at that point may be around zero. And that's why you see the astronauts floating, in the spaceship and what have you. And of course, depending on if they go to the moon, because the acceleration due to gravity of the moon is 1.63, very small. So they need to be dragging their feet because the force holding them to the moon is very small. So when you throw something, it can continue to go, okay, without falling down. Okay, so this is a special equation, which is W equal mg. It's a special equation, while the general equation is the Newton's law of gravitational equation, which is NLUG. Okay, this is just an example. And the Newton's second law of motion, summation of all forces acting on a body is equal to the mass times the acceleration. It's a general equation. Okay, but it is in vector form. Some special case equations can be derived from this, which is if you take x direction, y direction, you can derive the scalar equation. But the equation is generally in vector form. This, summation F equal MA, and that's why F and A are in bold. They are written in bold because they are vectors. Okay, so you can look at a particular direction X, Y, summation, to get the scalar equations, which are spatial case equations. So the general equation defines the mechanical work. This is another example, work in which is defined as the for a line integral of the first vector dotted with the displacement vector, and the associated spatial case equation is force times distance, where W is the force, R is the work, and F is the force, and D is the displacement. Now, coming back to stress, relating stress to force. We have seen the shear stress is given by the tangential force over the area, So when you look at a particle, an object, a body here where you have a flow, now this is the pressure distribution acting on all sides, How pressure varies from point to point along a surface. In this example, pressure is large at in front and low at the back. So the force is going to be the integral over the area, of all the force over the area acting, the small force acting on the small area, when you sum it up, because integration is summation, and multiply by the total area, in this case, dA, force over area over the incremental area. When you sum it over the area, you now have the total force acting, and the force over area is the definition of stress. Like now, if you isolate a single point, you have dF acting on this area that is vertical. dF is a force on a small area, dA, and N is a unit vector that is outward from a surface. Unit vector, it gives the direction of a force, simple. So here the unit vector is telling you that it is opposite to the force. The force is perpendicular to the surface area, and the unit vector N is outward from the surface, moving away. So it will have the direction of the force is opposite to that of the unit vector, so it will be minus. So dF now, if we want to define the dF in terms of the so it's going to be minus Pn dA. Pressure, by the way, is not a vector quantity, it is a scalar quantity. It is a scalar quantity because at the point, like pressure in liquid, it acts in all directions. It is not specific with a particular direction here or there. It only depends on the surface area in contact, but it is not dependent upon direction. Like this force, it will have components vertically and horizontally, and you will have different. But pressure at a point in, let's say, in liquid, for example, it acts the same value in all directions. In all directions. So it is not direction dependent. Hence, pressure is a scalar quantity, not a vector quantity. So force here is going to be the pressure times area. But here we put minus N to show that the direction of the force is in opposite direction to the unit vector. And again, we can that's why this is given in vector quantity. And then to get the total force, we need to integrate, isn't it? We need to integrate to get the total force, which is the force pressure, We need to integrate. And to simplify, this is the general equation, and the spatial equation is PA, that is pressure times area. And what are the assumptions? Because before you reduce from general equation to spatial case equation, you need to make some assumptions. Like in this case, we don't have N, we don't have minus, because what we are saying is that the force is perpendicular to the area and it is inward. Okay, it is inward, not outward. That's why we remove the negative sign. So we no need, because this negative sign, what it tells us that it is in opposite direction to the unit vector. Unit vector in statics, you were taught it is u, okay, and is given by the force vector over its magnitude. The magnitude of the force vector, okay? This is a unit vector. But the simple application of the unit vector, it gives you direction. But the unit vector is just one. Its magnitude is one. Okay? The magnitude of a unit vector is one. So meaning it is dimensionless. So the importance of a unit vector is it gives direction to a vector quantity. That is the importance. Okay? Not that it alters the calculation or anything, but tells you about direction, because a force vector, you need to define its direction. So unit vector are defining directions, giving directions to force vectors. Okay, and that's why here when we remove the negative sign, we now, okay, so the assumption here, moving from here to here, is that this area is flat. Okay, it is flat, horizontal, and then the force vector is acting inward, that is into the area. It is perpendicular and into the area, not inclined, because if it's inclined, then you need to solve it. Okay, so these are the assumptions I already explained. So still on relating stress to force, okay, when you have an object and you have a fluid flowing around it, there will be shear stress distribution. How shear stress varies from point to point. Okay, remember in the first case we defined pressure. Okay, and now we want to define the shear stress, which is having related to the tangential force. Okay, not the perpendicular force. The perpendicular force is the normal force. Okay, now the tangential force. Okay, acting on the area, we use the shear stress. Okay, we use the shear stress here. Okay, the shear stress. So the force now, the force acting, T is the unit vector that is tangent to the surface. Okay, that is tangent to the surface and in the same direction as the force vector. That's why you don't have any negative sign here, because it is in the same direction as the force vector. This is the unit vector. In the previous case, we use N. Now we are using small letter T. Okay, this is the shear stress, and then we can simplify it. I mean, we can make assumption, okay, to reduce it to this. Okay, and here it means that the force vector and the force vector is tangential and parallel to the area. Okay, it's tangential and parallel to the area. These are the assumptions. Okay, let me see what you have written so that I can. Oh, okay. My time is up. In the next class, I will go over this fluid properties, and then we move on. We move to viscosity. All right. Let me see. You save this lecture. Yeah, I will upload it now, but I will update it. I will upload it now, but just keep. I may update it. So once I update it, I will write in bracket updated. Okay. Yeah. My time is up. So if you have any question, please go ahead. Okay. In the absence of any question, we will call it a day. We see next week. But remember, next week we will have a quiz. We will have quiz just like today, okay? Because we are supposed to be having quizzes every 2 weeks. Every 2 weeks. And next week will be our second week. Okay? Next week will be our second week. So next week we will have quiz online. Okay? The quiz is going to be online. Okay? So get ready. Yeah, what day? The day is going to be Wednesday. The day is going to be Wednesday. Yeah. Yeah, it will cover up to where we stop today. Up to where we stop today. That is just before viscosity. Okay, up to slide number 37, 36, up to slide number 36. Okay, that's up to where we stop today. All right, thank you. See you next week.